Now we begin our discussion on vectors. Some things are measured simply by one unit, such as mass, length, or time. However, vectors are used to describe forces, displacement, and velocity, amongst other things. Vectors have both a magnitude and a direction. Here we see a vector. The vector has an initial point and a terminal point. You must go from A to B, hence there is a direction, and then we have a magnitude. A magnitude is the length of AB. So I have pulled in a definition. The vector AB here, represented by the segment AB, notice I've got this little directional arrowed line above AB, has an initial point where we start, A, and a terminal point where we end, B. The length or magnitude is denoted using those two bars. And we can always say that a vector or two vectors are equal if they have the same magnitude and direction. All right, so if you were asked to prove how two vectors were equal, you would need to show that they have both the same magnitude or length and the same direction or angle or slope. Here I've pulled in two pictures. What these two pictures illustrate for us is, say, a velocity vector, we'll call it v, at a specific location for a particle moving along a path. This is the vector at that moment on the path in a plane or in some 3 space. So it went forward, it looped around backwards and continued. So we can have vectors in a plane or in space, 2 or 3 dimensions. The arrowhead on the path indicates the direction of the motion of the particle. Here, let's talk a little bit about vector notation. So this blue vector is a vector from P to Q, and we would write that as PQ. We would put that directional arrow above it to say we start initially at P and we terminate or end at Q. Now, you'll notice we have this vector V, and you'll see V here is a bold lowercase letter. It's a boldface. So V is actually, try and make it look bold here, V is actually equal to PQ. They are not in the same location, but both vectors have the same angle or slope, direction, and they both have the same magnitude or length. Now, you'll notice V originates at the origin and it travels to some point in space, V1, V2, V3. Right? So we've got a horizontal on X, a Y, and then a vertical Z. Vector V is the same as vector PQ, but it's in standard position. And you'll notice we have these pointy braces here. We use these pointy braces when we have a vector that starts at the origin, and we can call this component form. So I could pick this vector up and move it somewhere else, and it would still have that same length and magnitude, but the component form says, hey, we're starting at 0, 0, 0 and traveling to some point X, Y, Z. So I've pulled in a definition here. If we have a 2D vector just in the XY plane with an initial point at the origin and a terminal point somewhere in that 2 space, then the component form of that vector would be those end points. And so this only works when we're starting at the origin. And of course, if it was in 3 space, starting at the origin, ending at some terminal point, X, Y, Z, we can say V, and we use these pointy parentheses or braces here to say V1, V2, V3. So this is component form. And a lot of the times we want to convert a vector to component form to do calculations. Component form makes vector calculations much simpler. Continuing along, we're going to add another formula or definition. So we'll start talking about magnitude. Magnitude's the same word as length. If we wanted to determine the magnitude or length of a vector lowercase bold v, which is equal to that PQ from an initial point and a terminal point, the magnitude, we're using those bars. Remember, those bars look like absolute value. Absolute value is the distance or space from 0. So the magnitude of v equals the square root of each the x, y, and z components. And if it's not in component form, we can find that by subtracting the x's, subtracting the y's, and subtracting the z's. So each of those components squared, square root. So this is really the same as our distance formula we talked about in the first section. I feel it is also important to note that we can have a 0 vector. So we could say a bold 0 is equal to 0, 0 in component form, or 0, 0, 0 in component form for 3 space, right? So we use this bold 0 to represent a 0 vector. And this is a vector, this is the only vector with no direction, and it has no length. So 0 length and 0 direction. For this example, we're going to find the component form as well as the length of a vector, and we are given an initial and a terminal point. My initial point is -3, 4, 1. My terminal point is -5, 2, 2. For the first part of this, I'll say A, we're going to find the component form. The component form is found, V1, my x component, would be the difference of my x's. So x2 or x sub 2 minus x sub 1, -5 minus -3, which gives me -2. V sub 2, my y component, would be the difference of my y values, y sub 2 minus y sub 1, 2 minus 4, which is also -2. And V sub 3, my z component, is z sub 2 minus z sub 1, or 2 minus 1, which gives us +1. Therefore, the component form for this vector, lowercase bold v, is -2, -2, and 1. So I subtracted my initial and terminal x's, y's, and z's to get my x, y, and z components. The x component, the y component, and the z component. If I'm asked to then find the length of the vector, we're just going to use our distance formula, essentially, the magnitude of this vector. So for B, since we already have it in component form, the magnitude of vector V is the square root of each component squared and summed. So my x component, -2 squared, plus my y component, which is also -2 squared, plus my z component, 1 squared. I end up with the square root of 4 plus 1, or the square root of 9, which is 3. So I have my vector in component form, and I also know the magnitude or length of my vector is 3. Let's look at an example. And this example talks about effective force. So I'm going to define what that effective force is before we begin. Given some vector, boldface F here, in component form AB, the effective force can be found by saying A equals that magnitude of vector F times the cosine of some angle theta. So what that represents, what A, that effective force, that's the force that's actually pulling the cart forward. So that's my horizontal component. You'll notice cosine is associated with what we might say is X. If we wanted to find the force that was actually pulling up, B, that vertical component, would be the magnitude of the force times sine of theta. So we have an example here. We have a small cart being pulled along a smooth horizontal floor. We have a 20-pound force pulling on it and making a 45-degree angle with the floor. What is the effective force moving the cart forward? So this is what is the horizontal component of that vector. And I've pulled in a picture to help us think about what we're looking at here. So here's our force. Our force is pulling this way at this 45 degrees off the horizontal from where it is attached, the handle per se, or where we are pulling. And if we want to find that effective force, what is causing the cart to move forward, that's going to be this horizontal component. So in this situation, A is equal, and when I say A, I'm referring to that horizontal component. A is the magnitude of the force, which is 20, times the cosine of the angle, theta, or 45. We know that cosine of 45 is root 2 over 2, so this simplifies to 10 root 2, or approximately 14.14 pounds, right? So even though we are applying 20 pounds of force, we're not applying it in essentially the most effective manner to pull it directly forward. We're pulling it at this angle, which causes it to be less than that 20 pounds. So in this video, we started talking about vectors. We talked about vector notation and component form. And then we mentioned or talked about how to find the magnitude of a vector and to break that into the components. So in Calculus 3, technically this is review. You saw much of this in trig, which you would have taken before you took Calc 1, Calc 2, and then now Calc 3. But I know quite a few of you probably don't remember it well, or maybe your instructor didn't focus on it as much. So moving forward, we're going to talk about vector algebra operations.